Welcome to our deep dive into one of the most fascinating and mysterious phenomena in the universe: white holes. You see, black holes get all the press, don't they? These cosmic monsters with gravitational pulls so strong nothing, not even light, can escape. But what about their flip side? What about regions of space where matter and energy gush outwards like cosmic fountains? That's what we're talking about today. White holes. Today we'll explore what they are, how they work, and much more. So, what exactly are we talking about when we say white hole? It's a term that sparks the imagination, conjuring up images of bright, energetic bursts in the vast darkness of space. You see, in the grand cosmic dance of existence, where gravity reigns supreme, a white hole is the theoretical antithesis of a black hole. Imagine a region of space-time where entry is forbidden, a one-way door flung wide open but only from the inside out. That's the essence of a white hole. Think of it like this: a black hole is a cosmic vacuum cleaner, relentlessly sucking in anything that gets too close. A white hole, on the other hand, is like a cosmic geyser, an unrelenting fountain of matter and energy spewing out into the universe. White holes emerge from the depths of Einstein's general relativity, the same theory that predicted black holes. According to general relativity, space-time is a flexible fabric, warped and stretched by mass and energy. A white hole, theoretically, is what lies on the other side of that singularity. Now that we have a basic understanding of what a white hole is, let's delve a little deeper into the theoretical mechanics behind these enigmatic objects. Imagine, if you will, the fabric of space-time as a vast cosmic sheet. Now picture a black hole as a bowling ball placed on that sheet, causing a deep indentation. Now, instead of a bowling ball, imagine an object with negative mass, something that repels matter instead of attracting it. This hypothetical object would create a bump in space-time, a region where the fabric is pushed outwards instead of inwards. This, my friends, is one way to visualize the theoretical formation of a white hole. Stephen Hawking proposed that black holes slowly radiate away their mass over time through a process known as Hawking radiation. Eventually, a black hole could completely evaporate, leaving behind, well, that's where things get really interesting. Some physicists speculate that the endpoint of a black hole's evaporation might be the birth of a white hole. Now let's take a giant leap from the theoretical workings of white holes to one of the most profound questions in cosmology: the origin of our universe. The Big Bang Theory, the prevailing model for the birth of our universe, posits that everything we observe today originated from an incredibly dense and hot singularity. This singularity, some scientists speculate, might have been a white hole itself. Think about it. The Big Bang was an event of unimaginable energy and expansion, with matter and energy seemingly erupting from a single point. Doesn't that sound eerily similar to the theoretical description of a white hole? The idea that the Big Bang was, in essence, a white hole is a tantalizing one. It offers a potential solution to the singularity problem that plagues the Big Bang model. If the Big Bang were a white hole, it could potentially sidestep the singularity issue. Of course, this is all highly speculative. So, imagine for a moment that we could travel across the vast cosmic ocean and stumble upon a white hole. Could we perhaps venture inside like explorers stepping through a portal to another dimension? Well, according to our current understanding of physics, the answer is a resounding no. You see, the very nature of a white hole's event horizon prevents anything from entering from the outside. Imagine you're a tiny spacecraft approaching a white hole. As you get closer, the curvature of space-time becomes increasingly extreme. The closer you get, the faster you would have to travel just to stay in place, much like trying to run up a downward-moving escalator. At the event horizon, the point of no return for a black hole, this effect becomes infinitely strong. Even if you could travel at the speed of light, you could never overcome the outward flow of space-time at a white hole's event horizon. It's safe to say that a close encounter with a white hole would be a one-way ticket to oblivion. So far, we've journeyed through the theoretical landscape of white holes, exploring their potential properties and implications. But the question remains, are these cosmic fountains of energy and matter actually real, or are they merely figments of our mathematical imaginations? Well, I'll be honest with you. The existence of white holes is still very much an open question in astrophysics. While general relativity predicts their existence, we haven't found any concrete observational evidence to confirm their presence in the universe. Observing a white hole directly would be incredibly challenging, even more so than observing a black hole. While black holes warp space-time and gobble up light, making them detectable through their gravitational influence and the absence of light, white holes are theoretically brilliant beacons of energy, constantly spewing matter and light outwards. However, just because we haven't spotted one yet doesn't mean they're not out there. As our observational tools and techniques improve, we might one day find ourselves face to face with evidence of these elusive objects. Now, while we haven't definitively observed a white hole, there have been some intriguing observations that have sparked debate and fueled speculation about their existence. One such observation involves gamma-ray bursts, or GRBs, the most powerful explosions in the universe. These incredibly energetic events release more energy in a few seconds than our sun will emit in its entire lifetime. Some scientists have proposed that certain types of GRBs, particularly short-duration GRBs, could be the signatures of white holes forming. Another intriguing observation involves a phenomenon known as fast radio bursts, or FRBs. These are extremely brief, intense pulses of radio waves that originate from distant galaxies. While the exact nature and origin of FRBs are still debated, some scientists have suggested that they could be linked to white holes. However, it's important to note that these are just potential interpretations of complex observations. We've explored the potential observational fingerprints of white holes, but what about their formation? How does the universe even go about creating these cosmic fountains, these regions of space-time where the exit door is wide open, but the entrance is forever sealed? The formation of white holes is still shrouded in mystery. Remember, we're dealing with objects that push the boundaries of our understanding of physics. One possibility, as we've touched upon earlier, is the Big Bang itself. Some theorists propose that the universe's explosive birth from an incredibly dense and hot singularity could be the ultimate example of a white hole. Another intriguing possibility lies in the realm of quantum mechanics, the strange and counterintuitive world of the very small. Quantum fluctuations, tiny energy fluctuations in the vacuum of space, are thought to be responsible for the spontaneous creation and annihilation of particles. Some physicists believe that under extreme conditions, such as those found near a black hole's singularity, these quantum fluctuations could become powerful enough to create a white hole. Another idea involves the theoretical endpoint of a black hole's life cycle. The study of white holes, while deeply rooted in theoretical physics, is a relatively young field. However, over the years, numerous brilliant minds have contributed to our understanding of these enigmatic objects. One of the earliest pioneers in the study of white holes was physicist Roger Penrose, known for his groundbreaking work on black holes and general relativity. In the 1960s, Penrose proposed the concept of white hole horizons, regions of space-time from which matter and energy could only escape, never enter. Another prominent figure in white hole research is physicist Stephen Hawking, whose work on black hole evaporation we've discussed extensively. More recently, physicist Carlo Rovelli, a proponent of loop quantum gravity, has explored the possibility that white holes might emerge from the quantum realm, specifically from the quantum fluctuations near black hole singularities. These are just a few of the many brilliant minds who have dedicated their careers to unraveling the mysteries of white holes. Their work serves as a testament to the power of human curiosity and our insatiable desire to comprehend the cosmos. Thank you for joining us on this journey through the cosmos. We've delved into the heart of one of the universe's most enduring mysteries, exploring the theoretical landscapes of white holes, from their potential origins in the Big Bang to their hypothetical formation from the remnants of black holes. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating content about our universe. Until next time, keep looking up.